My lovely TAs are here. Hey, Dheeraj, Nashikar. What's that? I'm not moving. What's going on? Yeah, check with. I'm not even moving. It's crackling even while I'm not moving. Okay. No, but that's not picking up stuff from my mouth. It's just my motion is causing it to crackle.
Yeah, you have something in your pocket there, like a
Nothing.
phone or anything?
Nothing.
I think it's fine. Try moving around.
1, 2, 3. Okay. All right, everybody. Let's start. This is the last of our series of lectures on convolutional neural networks. We're going to be completing the business on back propagation through a quick recap with completing the series on back propagation through convolutional networks. And we'll look at a few modifications of convolutional neural networks which allow different kinds of invariances and how mechanisms for variance on convolutional neural networks, and then mechanisms for deriving more information than just basic classification itself using CNNs. So the story so far is that shift invariant pattern classification tasks, such as does this picture contain a cat or does this recording include hello, are best performed by scanning for the target pattern using CNNs or time delay neural networks. What was the difference between CNNs and time delay neural networks? The number of dimensions. For time delay neural networks, you just scanned along one dimension. Convolutional neural networks scanned along both dimensions. We also called time delay neural network something else. What was that? We just called it a 1D CNN, right? And so these are shared parameter models that can be trained using variants of back propagation. So we saw how this could be done. We need to compute gradients, as in the case of regular MLPs, except we must consider the fact that the different parts of the network, the CNN is effectively the equivalent of scanning with an MLP, but that is also effectively the equivalent of one giant network where different subcomponents of this giant network have identical parameters. And so we must modify our gradient computation to account for the sharing of parameters. And instead of just explicitly accounting for the sharing of parameters, we just saw how the math worked out. And we found that all we had to do was to make some changes to how derivatives are computed. Now, typically, we just pass the training data through the network. We'd compute a loss, which quantifies the divergence between the actual output of the network and the desired output. We back propagate its derivatives through the net. We know how to do it through an MLP, so that would bring us the derivatives all the way. Now again, recall that a CNN comprises many layers of convolutional layers, many convolution and pooling, which could alternate. You can have pooling layers will typically follow convolution layers, but they're not mandatory, right? And so your CNN looks something like this. You have several layers where you compute maps. The final maps are flattened and passed through an MLP. So when you train the network, we would compute your loss out here, back propagated derivatives until here. And then from here, you would fold all the derivatives back into the shape of the final maps, the maps of the final layer of the convolution, the final convolutional layer, and then continue to back propagate derivatives from there. And so here, what we needed to find was, given the derivatives for the output, the loss derivatives for the output of a convolution layer, how do you propagate them back to compute derivatives for the activation maps from the affine maps from which the activation maps are computed, and then how to go on from there to compute derivatives for the filters and the derivatives for the input maps to the convolution layer. And for pooling layers, we had to figure out how to compute derivatives with respect to the input to the pooling layer given the derivatives with respect to the output of the pooling layer. And for the convolution layers, we saw first how to compute the derivatives for affine maps given the derivatives for activation maps, which is simply performed by a pointwise backpropagation, where you simply multiply the derivative for the affine term by the derivative of the activation function itself. And then for the passing the derivatives of the affine maps back to the filters and the previous layer, we had to do something a little more fancy. If we wanted, again, the affine maps within any convolution layer are computed from all of the input channels, all of the input maps. And how many, what was the relationship between the number of output affine maps and the number of input channels and the number of filters in the coordinate system, but the numbers? How many output maps did we have? The number of filters, right? And so, but then how many channels did each filter have? The number of input maps. So that was a structural relationship. And so if we wanted to compute the derivative for an input map, we had to pick up the corresponding channels for all the filters. And then what did we do? Pardon me? We transpose these maps, right? We flip them left to right and top to bottom. So the whole thing is a transposition. If you think of the filters as this big cube, right? Four-dimensional cube, right? Over here. Because the number of filters is one dimension, then that's like transposing the entire tensor and then picking, and now you're working with something else, right? As a transpose of the original. So you'll be picking up the row of channels, and now you're flipping it, and now it becomes a column, right? And then within each column, you're flipping each map left to right, top to bottom. So there's a whole lot of flipping happening, which is basically transposition. Just as when we were performing back propagation through the MLPs, what was a direct multiplication going forward ended up being a transposition going backwards, right? So and then once we flipped we selected the filter channels and flipped them. Basically, once we transposed the filter, what did we do next? What did we do next? We convolve. We have the Pokemons. That's okay. Somebody on Zoom, what did we do next? Anybody? Is there anyone on Zoom?
Yeah.
Okay. So, Magnemite, what was the next thing we did? But what was the actual operation we performed?
Convolution.
We convolved the transposed filter with the derivative maps of the output affine terms, correct? So, and this gave us the derivatives for what? Pardon me? Yes, Katrina? For the yl minus 1, right? Then the next term we wanted to compute was the derivative for the weights and the filters. How did we compute the derivatives for the filters? Pokemon Flareon. So, Pokemon Flareon, how did we compute the derivatives for the weights? Okay. Drowsy. Pokemon Drowsy, yes, very appropriate for this time of the morning. How did we compute the derivatives for the weights?
We took the transpose.
did we transpose anything for the derivatives for the filters? How did we compute that?
Oh, I'm not sure.
Okay, so that's a fair answer. Chansey, Pokemon Chansey, what did we do?
I'm not sure either.
Okay, so Pokemon Remoraid, what did we do?
We can just convolve the derivative with every output.
With every we convolve the input maps directly with the derivative maps, right?
Yeah.
So if we convolve the derivative map for each output channel, when convolved with the entire set of input channels, gave us the derivative for the filter, which computed that particular output channel. And so this was very simple, computing the derivatives for the filters, right? So yeah, thank you, Remraid. Now, and so we have managed to compute derivatives for all of the convolution layers, so all components of the convolution layer. The next was computing derivatives for the pooling layers, right? And again, the pooling layers, if you were performing max pooling, you simply grouped or pooled groups of values to reduce jitter sensitivity, and you could pull this in one of two ways, one of several ways. The most common one is picking the max, right? And so you'd just scan left to right. At each point, you'd pick the max from the group that you're considering. And picking the max was broken up into two steps, the way we implemented it. So how did we, what were the two steps? Pokemon Visma. What were the two steps? That's Pokemon Visma. No? Okay. Pokemon Shift Tree. What were the two steps?
We use d div dy if the KL equals to the location in the pooling map.
And that was the first.
And 0 otherwise.
Okay, so but we decompose this into two steps, right? So what were the two steps? Somebody else?
We check if the value is the same.
Right now, so the two steps, just to clarify, in the first step, we identified the location of the largest value, right? And the second step, we just copied the value at this location into the output. So Pokemon Shift Tree, does that ring a bell?
Yeah.
Yep, right? And why did we do that?
For the back propagation.
For the back propagation, right? So basically, we needed to know where each element, output element, came from, because we know that the rest of the elements don't really influence the output. And so their derivatives are going to be 0. And then we can just copy it over. Now, if there are multiple input elements which have exactly the same value, both of them can just take the same derivative because we have nothing to choose, right? And so the way we did the back propagation for the max pooling, in the forward operation, we picked up, at each location, we found the location of the largest value and then copied that value over. During back propagation, we just copied the derivative value over to the location of the largest value. But then this was incremented rather than just overwritten, because the same largest value could be active in multiple positions, right? And the next one was mean pooling, where instead of just picking the largest value, we chose the average of the instances within the little group. And this is what we scanned with. In this case, how did we back propagate the derivatives? Pokemon Jigglypuff. Jigglypuff. Okay. Pokemon Scissor. Yes.
I think it's
Basically, we just we distributed the derivative uniformly over the entire input region, right? Divided by 1 over k squared. And once again, this was incremental because adjacent windows might overlap. And so here's what the forward operation for mean pooling was. At each location, you pick the mean of the block, and then in the backward propagation, we just copied the derivative of the output over, or incremented the derivatives at all of the locations, all of the elements used in the computation of any given output element by a fraction of the derivative of the output, where the fraction was basically the derivative divided by the number of elements, k squared, right? So far so good. Now, again, this was something we pointed out, that basically when we were performing mean pooling, the back propagation was essentially a channel-wise convolution of the derivative of the output map with a uniform filter. Now, this is something that I would actually like you to keep in mind. Was there a chalk here? Okay. Because we will see this being used elsewhere as well. And so you had YL. Each map was mean pooled to give you YL plus 1. Now, when you came backwards, these things were, so every single input map created its own output map, right? And then when we are back propagating, we basically took a filter which was where each element was 1 over k squared, and then scanned with this, and that gave us the derivatives going back, right? And this was done channel-wise. Within each channel, you are basically convolving the derivative map with a filter of all uniform sets of values, 1 over k squared. That makes sense, right? This was now we're going to, so again, the key over here is channel-wise convolution, except we are going backwards, right? So far, so good. We know how to do everything with convolution layers and pooling layers. Now, there was one other kind of operation that we haven't actually touched upon yet. Which was that?
Flatten.
Pardon me? So the person on Zoom who replied, can you please repeat yourself?
The flatten layer.
The flatten. Flatten is just reshaping. There was another key operation. Yes, someone mentioned here.
Is it
Downsampling and upsampling, right? The resampling layers. So, but first, let's go through this pool. Five seconds, guys. Okay. Pokemon Lombre. What is the answer to the first question? Okay, Pokemon Lomba. Oh, probably mispronouncing it. Pokemon Slowpoke. This is easy. What is the answer to the first question? Slowpoke.
Yeah, I was Lombre, but first one is true.
First one is true. That's Lombre, right? And Slowpoke, are you around? No. Okay. Pokemon Geodude. What is the answer to the second question?
It's true.
True. Okay, thank you. So when back propagating through a max pooling layer, derivatives from the pooling output back propagate only to the position of the largest input within the input pooling window for that output. when back propagating through a mean pooling layer, derivatives from the pooling output are distributed uniformly over the input pooling window for that output, right? So now the remaining layers are the resampling layers. Upsampling and downsampling can increase or decrease the size of the map. So upsampling followed by a convolution can be viewed as convolution with a fractional stride. And convolution followed by a downsampling can be viewed as convolution with a stride greater than 1, right? So, how do we back propagate through these layers? Again, you'll recall that I mentioned that anytime you perform convolution with a stride that's not equal to 1, it's more convenient to think of it as a sequence of operations. If you're performing any operation with a stride greater than 1, what is the correct way to think about it? Convolution or pooling with a stride of 1 plus downsampling, right? And if you're doing it with a fractional stride, what is the correct way to think about it? Upsampling followed by the operation, right? So easy. And now that means we want to think about the downsampling. We can just separate the resampling layers out from the basic operations itself. And now, here's the first rule. I can think of resampling, up or downsampling, as a layer, right? It's an operation all by itself. Now, this is my resampling layer. I have an input of some size, and this results in an output of a different size. It could be the same, it could be larger, or it could be smaller. It doesn't really matter, right? For the purpose of this particular concept. And this eventually gives you my divergence, my loss. So when I'm back propagating this derivatives out here, what is the size of the derivative map here going to be? The same as the?
Divergence.
It's going to be the same as the output, right? But then when I propagate it back further through this resampling layer, what is the size of the derivative map going to be? The same as the input. If you've got a certain number of values that are used to compute a function, when you compute the derivatives backwards, the number of derivatives is going to be the same as the number of variables that were used to compute the function. This doesn't mean that the derivatives are all going to be meaningful. Several of them could be 0. But the actual set of values is going to be the same size as the set of values that went into the function, right? Into the operation. Now this has got to be, this is a fundamental property that we're going to be using. So now, if I am downsampling, here's what I've got. When if I'm downsampling, I have some input over here, let's say something of this kind, right? And this goes through a downsampling layer. So when I'm downsampling, I'm going to be, let's say I'm downsampling by a factor of 2, right? So if I'm downsampling by a factor of 2, I'm effectively ignoring every alternate value. So I'm ignoring these guys, I'm ignoring these guys, I'm ignoring these guys, and I'm ignoring these guys. And so this goes through my downsampling layer, and this is going to give me, in this case, a 2 cross 2 map, right? So now when I'm computing my derivatives backwards, how many elements must the derivative map have? 16. It's going to have the full 4 cross 4, even though at the output, I only had 2 cross 2. But then, do these guys, which were ignored, influence the output? So what will their derivatives be? 0. So all of these guys are going to be 0, right? So, shoot. Correct? And what about the remaining guys? What are their derivatives? It will be the same as the derivative at the output, because perturbing this has the exact same effect as perturbing this element, right? So this can be just copied here. Similarly, perturbing this element here will have exactly the same influence as perturbing this element. So this can be copied here, right? And so you get your derivatives, you get your derivative map. What does this operation look like? Upsampling. So the derivative of a downsampling layer is simply upsampling, right? Isn't that beautiful? So here you go. The way I would do it, the gradient over here, we're speaking of the gradients of the divergence with respect to any variable is going to be, I'm speaking of gradients rather than derivatives, because gradients are the transpose of the derivatives. And the gradients are the same shape and size as the original variable. The derivatives are the transpose. But then when you get into tensors, who knows what the transpose looks like? So it's more convenient to think about it in terms of gradients, just to establish terminology, right? But then the gradient over here is going to have the same size as what went into the operation. And so my first step going back is I'm going to just allocate the derivatives of the appropriate size, because I know that's what the derivatives must be. And then I know many of these derivatives are 0. These values can just be set to 0, right? And the rest of them are just going to be, these are all 0. And the rest of them can just be copied over. Very straightforward. So this is just the back propagation through a downsampling layer. So the back propagation through downsampling is trivial. The derivatives for convolution are also trivial if you think of it as a convolution with a stride 1. So yeah, just copy these values over, right? Pseudocode is trivial, but once you understand the concept, it's straightforward. And anyway, the derivatives for convolution are simple. The derivatives for downsampling are also very simply computed. But if you try to directly compute the derivatives for convolution with a stride of 2, you're going to find yourself getting twisted into little knots. Whereas if I decompose it into a sequence of 2 operations, that becomes a non-issue, right? Especially because computing derivatives through a downsampling layer is very trivial, right? Now let's consider the other side. Let's consider upsampling. How do you think upsampling would work? So let's say I have an input map, which is 2 cross 2. Okay, and I'm upsampling it by 2. What is the output size going to be? Upsampling by 2. 4 by 4, right? I mean, I'm assuming that I'm introducing a spurious, correct? So if I'm upsampling by 4, if I call these A, B, C, and D, what values will I have over here? This is A, this is B, this is C, and this is D. What about the rest? They're all zeros, right? And this can be used to compute my divergence. Now, when I compute my derivatives going backwards, will I have zeros at these locations going backwards? No, right? This is just straight regular. This is just regular back propagation. You're going to get a derivative value at every location, right? But then when I go far backward from here, right, what do you think the derivatives are going to be?
Corresponds to the downsampling.
Yeah. Anybody else? Yes, Mokik is right, but since he mumbled, this gives me the benefit of restating the question, re-asking the question. What do you think the operation going backward should be?
Downsampling.
Downsampling, right? And why is that? Regardless of what derivative I get over here, is there anything that I can vary in the input that will change this value here? No, because that was going forward, that was always set to 0, right? Which means that this derivative is just, it's sitting here, it's not really doing anything useful for me. It has no connection to the input. Every one of these derivatives which were computed going backwards are kind of spurious as far as the input is concerned. They are not influenced by the input. There's nothing that I could vary in the input that would directly influence these parameters. There's no chain rule to be had, right? And therefore, so that means the derivative of any one of these values with respect to these guys is 0, which means there's nothing going on. What about these terms? What is the derivative here? Because perturbing this by any value is going to perturb this by the same value, right? So now what would the derivatives going backwards be? I just downsample. I just pick these derivatives and set all of these guys to 0 and copy it over, right? Very simple. So once you begin thinking about it in these terms, then the process of computing derivatives becomes very trivial, right? Now, again, if you go on the web and look for fractional strides or upsampling with fractional strides, they will call it transverse convolution and give you a lot of very pretty pictures. And the math is usually right, but then if you work through the whole process step by step as you would for fractional strides, it ends up looking kind of ugly and tedious. But then once you decompose it like so, it becomes a very trivial operation, right? So again, doing math right is often not about bludgeoning your way through the solution. It's about knowing how to break the problem up. So an upsampling layer simply introduces s-1 rows and columns for every map in the layer, effectively increasing the size of the map by a factor s in every direction. So it's used explicitly to increase the map size by a uniform factor. We know this. So back propagation, given the derivative of the divergence with respect to the elements of the output of the upsampling, we want to compute derivatives with respect to every element of the input to the upsampling. So because the derivative map should have the same size, or the gradient map should have the same size as the original input. And so we know that the 0 elements introduced during the forward pass are not functions of the input. They're always introduced as 0, regardless of the input. So the derivative of these 0 elements with respect to the input is 0. So they will have no influence on the input, have no influence on these values. And consequently, the derivatives here are going to have no influence on the derivatives of the input going backwards. You just copy the rest over, pretty much. And that's straightforward. So you back there, can you shut your laptop? Can you shut your laptop? Thank you. Right. So we just copy these derivatives over, right? Now, any questions? Questions on Zoom? Any questions, folks? It's very straightforward, nothing particularly complicated, right? And so back propagation through an upsampling layer is a very trivial operation also.
Question?
Yeah. Go
Yes,
ahead.
yes. It's about the max pooling. In the assignment, they said that we can view the max pooling as a simple convolution where we will put maybe 0 everywhere in the filter and 1 where we have the position of the maximum value.
So strictly speaking, it's not a convolution because max is not a linear operation, right? Mean pooling is a linear operation. You can call it, so it's a convolution. You can view it as a convolution with some strange operations going on inside each block. So if you think of scanning as a convolution operation, then it's a nonlinear convolution operation. But as traditionally defined, convolution is basically scanning with a filter. Okay. So,
okay, thank you.
Now, again, convolution, we said, is often performed with a stride larger than 1 to result in a smaller output map. Oh gosh. So this, for purposes of backprop, it's easiest to view this as convolution followed by a downsampling layer. And this makes the computation of derivatives essentially trivial, because back propagating through a downsampling layer is super simple, right? Very trivial, very trivially simple. Just back propagate first through the downsampling layer, because the downsampling layer follows the convolution operation, and then back propagate the result through the convolution layer, the derivatives of the result, the convolution layer. Convolution can also be performed with a fractional stride, which increases the size of the map. And this is best thought of as upsampling followed by a convolution with stride 1. And once you do so, then once again, back propagation becomes a very trivial operation. You back propagate through the convolution and then back propagate through the upsampling layer, right? So for purposes of backprop, it's easiest to view this as an upsampling followed by convolution. Now, pooling is, we're going to find a lot of terminology on the web and a lot of very interesting explanations for how you can back propagate through layers which have stride not equal to 1. They're all correct, but then conceptually speaking, they're not adding anything more than what we've just seen. What they are telling you is, tedious results where you're trying to maybe optimize computation, right? Now, pooling is typically followed by performed with strides greater than 1 also, like so. This results in a shrinking of the map. So pooling is almost always performed with stride greater than 1. But then for our purpose, once again, if you simplify everything, you can say pooling is followed by with stride greater than 1 is pooling with stride equal to 1, followed by downsampling. This is particularly relevant if you're performing mean pooling, because that's mean pooling, the derivatives computation for mean pooling is just simple convolution, right? And so, but then here's something magical about the whole thing. We sort of went through the math. We went through the math for back propagating through a convolution layer. We went through the math for back propagating through pooling layers, through upsampling, downsampling, and whatnot. But the simplest way to actually think about these things is often just purely mechanically, right? What are we calling these operations? What did we call this whole business of passing derivatives, computing derivatives? We called it back propagation, right? What does this imply? Computation performed in reverse, right? So I can actually pretty much collapse everything to this very simple idea, which is this. That if I have y equals some ax, right? And then I have loss equals some function of y, then what is d loss over, given d loss over dy, what is d loss over dA? What is this? Anyone? So Pokemon Mantine, what is this?
It's d loss over dy times dy over dA.
Which is?
D
What is
loss
d?
over dy times
Yeah,
dy over dA.
and what is dy over dA? I'm starting with
X.
x, correct?
Yes.
So x. And just in case we are reusing values, I can just say plus equals, right? And what is d loss over dx? Pokemon Stantler. What is this? What is d loss over dx? Pokemon Stantler? All right, Pokemon Fiero. What is this derivative?
I think it is d loss over dy times x. Times a, sorry.
Beautiful, right? So this is, I can put a plus equals. This rule is trivial. Does anybody find this to be complicated? Not at all, right? Let's go and look at the code. So this is my code for convolution going forward. I've just made it very explicit, right? So what are we doing? We are scanning left to right. I've written this as a scanning NLP. It should have been the other way. The layers would come first. The scanning would be on the inside, but it doesn't really matter, right? So you're scanning left to right, top to bottom, then you're going through the layers. And then at each position as you scan, you're first computing an affine value. So what we are doing is, as we scan the input, right, I have an input, and I'm scanning, but at each position, I'm computing a dot product also. And for the dot product, I have a bunch of filter parameters. I'm multiplying them with the underlying input value and summing them up. So the dot product itself is a little scan, because I'm scanning over the filter, right? If I think of it that way. So here's what I am doing. I'm going through the filters. Within each filter, I'm scanning the window. And at each position, all I'm doing is multiplying, adding the, incrementing the affine value by the product of the weight and the input. When the whole thing is done, I'm just putting that y through an activation. So I've got to fix this, the indices over here. Can you take note? Yeah. So now, if I'm back propagating, what do you think will happen? I'm going to perform the entire operation in reverse, right? So all I will do is just flip this code. Look at what happened to how the indices go over here. The indices are going from 1 to W, 1 to H. Then I'm going over the filters. Then within the filter, I'm going over the width of the filter, and I'm going over the height of the filter. And then at each location, I'm multiplying by, I'm incrementing by the product of W and Y, right? And then finally, now, if I go back, this Y is being computed outside the window loop, right? So again, Y is activation applied to Z, right? So the other rule that I'm going to use is if Y equals A of Z, then what is dL over dz? This is going to be dL over dy times f prime of z, right? This we are good with? So I'm just going to change this code very trivially. I'm going to reverse the order of the indices. Instead of going from 1 to max, I'm going down from max to 1, right? And the first thing I did was, since y was at the y computation is being performed at the end of the loop, I repositioned it, and the computation of the derivative for z went to the beginning of the loop, just outside the window loop, so that I have the dz's, right? Easy enough for every z. That's easy. And then in here, I just use this simple rule. I just use this combination of rules, right? And I said dl over dy is w times dz, and dl over dw is y times dz, whatever terms I was multiplying. So look at this carefully, right? Here I've said zxy equals wx prime y prime plus y times x minus x prime, x plus x prime minus 1, y plus y prime minus 1. Look at the indices carefully, right? When I'm going backward, I'm retaining those indices. All I have done is to say, therefore, the derivative of y at x plus x prime minus 1, y plus y prime minus 1 is incremented by wx prime y prime times dz, right? And the derivative at w at x prime y prime is incremented by y at x plus x prime minus 1, y plus y prime minus 1 times the derivative dz, right? Do you see how little change I performed in the code? Essentially none. It's the same code. What was on the left came to the right. What was on the right came to the left. I just reversed the order of the computations. Everybody see what happened here? And that's it. All the math that I gave you over 2 lectures was replaced by this one little piece. So I need not have done all of that. I could have just done this, and you'd have learned just the same amount, but maybe not quite understood what was going on.
Okay, yeah.
Right? And so if I'm doing this with a stride, so this makes things even simpler, right? You can go through pages and pages of math, or you can decompose things into convolution layers and followed by downsampling, upsampling, followed by convolution, etc. But you don't even need to worry about it. You can take whatever operation you were performing in the forward pass and just use the same logic. So if I was performing convolution with a stride, this was what was happening going forward, right? The same operation, when I was performing convolution with a stride, I was looping left to right, top to bottom, except I was looping with a stride, right? And so when I go back, but within the window, of course, the stride was 1, because when you're computing the inner product, the stride is 1, right? And so when I'm going backward, I'm just going to flip the order. I was going forward with a stride. I'm going to go backward with a stride. But the rest of the operation in the innermost loop stays exactly the same. Nothing changed, right? I took what was on the left and put it to the right, what was on the right and put it to the left within the innermost loop. And I get the same derivatives. So code-wise, this was trivial. Yeah.
Essentially, coming backwards, you just hop from the stride.
Exactly, that's all you do, right? Hop backwards using the same stride. So is this making sense to you guys? Questions? Any questions? So looking at this through code and exactly how you implement stuff can make things trivial to do even if you don't fully understand the underlying math, because you know you're right. And the key to this lies in understanding the term back propagation. The derivatives go backwards, which means the loops go backwards, everything goes backwards, right? Specifically over here, it doesn't even matter if you change the order of the loop, if you're striding backward from end to the beginning, because the values at the various positions don't really interact with each other. So even if I had the strides going the same way, if all I changed was what was happening in the innermost loop, like so, the computation of derivatives would still work, right? So, I mean, if you look at the code, you will find that for the outermost loop, whether I'm going from the first position to the last position to the first, nothing really changes, right? The one extra difference is that the derivatives are now being incremented. They should first be initialized to 0. Everything is initialized to 0. And then you keep incrementing the derivatives to make sure that variables that are reused are properly handled, right? So same thing for max pooling. Here's what we were doing going forward, right? You can just, with a stride, we can reverse the process, just redo the code. Mean pooling, the mean pooling is, as we saw, computation of derivatives is just like, mean pooling is like convolution, right? So you can just flip the order, and the same logic as before also holds. Yeah. Five seconds, guys. All right, time's up. Pokemon Gengar. What's the answer to the first one?
It's true.
It's true. Thank you. And Pokemon Lapras. Lapras, is it the correct pronunciation? What's the answer to the second one?
It's true.
Thank you. And Pokemon Sandslash. What's the answer to the third one? Sandslash. So Pokemon Sandslash is missing. Pokemon Steelix, what's the answer to the third one?
Oh, it's false.
It's false. Perfect, right? You guys have got the whole idea. That's amazing. Now, the backward pass of an upsampling layer is downsampling. The backward pass of a downsampling layer is upsampling. We can simply use an upsampling layer as the backward pass of downsampling and vice versa. Why is the last one false? That was a brilliant answer, but why? Why is that?
Is it because of the shape? Like
Because of the shape, right? You can get an extra 0 when the backward pass of a downsampling layer. You got to figure out whether you're adding an extra layer of zeros at the end or not, and this can vary, right? So the answers can be very different, although conceptually the upsampling and downsampling are complements of one another. So in particular, Steelix, that was a brilliant answer. All right, so we've shown how we can compute the derivative with respect to every intermediate term, every free parameter, and so now all of this can be embedded into gradient descent, and you can use this to learn the network. So the story so far: convolutional neural networks are supervised versions of computational models of mammalian vision. They include convolutional layers comprising learned filters that can scan the outputs of the previous layer, and downsampling layers, or actually I should have said pooling layers, that operate over groups of outputs, and they're typically combined with convolutional downsampling. As viewed in the model of the mammalian vision, pooling is not distinctly viewed from downsampling. We did that for mathematical and computational purposes. So you have the traditional downsampling layer actually refers to a pooling layer. The parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum. Other pooling operators can use regular gradients, or if you have some crazy functions in there, subgradients. And we also saw that the derivatives are always going to be incremented because they must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter model, right? So far so good. We saw that CNNs are shift invariant models. But then somewhere along, very early in the class, some of you asked me a question. What about scaling? What about rotations? How does it deal with scaling and rotations? And so how can we deal with this? Now, this is a kind of Socratic question. I don't expect you to know the answer. But if you were to be faced with this problem, how would you deal with, say, rotation invariance? Anyone?
Pre-process the data set.
You can pre-process the data set. You can increase your data set to include all kinds of rotations. But suppose you don't want to do that. Suppose you want to do it algorithmically. How would you do it?
You just rotate it to like a.
Pardon me?
Rotate it back.
You rotate it back. So you're giving me some answers, right? If I give you lots of data with all kinds of rotations of the patterns, can I use a network of the same size as before? No, because I'm going to need more filters to account for the different orientations. If I do not want to do that, then what would I need to do? Anyone?
Can you make your kernel itself rotationally symmetric?
Fantastic, right? That's exactly what you would do. So we're going to rotate the kernel. So here's what shift invariance would do, right? You have a kernel, and the kernel must produce this, the filter must produce the same result regardless of where it's positioned. So basically, you can just say that you can think of this as shifting the kernel and applying it at each location. That's how shift invariance was created. We used the same kernel and shifted the kernel, and as a result, you got the same response at different shifts of the kernel, and therefore you got shift invariance, right? So just using the same principle, if I want rotation invariance, what would I do with the kernel? I would rotate it, right? I'm going to take my kernel, and I'm going to, if I want invariance to, say, a 45-degree rotation, I'm going to rotate my kernel by 45 degrees and then scan with it. right? So, and now this model is going to be invariant to rotations and shift. But what kind of rotation is it invariant to? Explicitly for 45 degrees, right? Nothing else. So if I want to have a whole bunch of different invariances, I want invariance to reflection. I want invariance to a 45-degree rotation. I want invariance to a 90-degree rotation. I want invariance to a rotation of minus 45 degrees. Every one of these transforms is something that I must explicitly consider at each layer. Each kernel must be rotated through a transform through all of these transforms, and each one of these transformed variants of the kernel must now scan the input, which means that if I have n transforms that I'm considering, and if I have a single kernel, in the absence of transforms, a single kernel is going to produce just one output channel, right? A single filter. But if I'm now introducing transformations of these filters, if I have, say, n transformations that I want invariance for, how many output channels would a single filter produce? Anyone? N, right? Every transform of the filter is going to produce its own map. So you have the original channel, original filter producing an output channel, but then the 45-degree rotated version of the filter producing another output channel, the 90-degree rotated version of the filter producing yet another output channel, and so on. So this thing is going to build up very quickly, right? So here was a regular CNN within a single layer. As you were scanning the inputs, at each position location, you're just going through all of the kernels, all of the filters in the layer, and processing the input with each of these filters. Now, as you go through the filters, you're going to be transforming the filter using each one of the transformations that you want invariance to, and scanning with each of these guys. Yes, Chetan?
How does the shape of the filter from like straight to like?
That you would have to compute, right? You'd know how to, you need to have some mechanism for rotating the filter. And that's going to be, that's actually an interesting question. We'll get to that in a minute, right? What is a 45-degree rotation? Mathematically, we know what the operation is, correct? But now you're not looking at a continuous object. You're looking at something. A filter is basically a pattern of 4 numbers, right? So if I want to rotate it by 45 degrees, how do I do it? It's basically just a map, right? I'm going to have a new filter, and I'm going to have some function which tells me how these filter values can be used to compute the new values, and that function itself must be differentiable, or it can be, if it's a, if I'm looking for some kind of reordering, it can just be a table, right? But these are being explicit. These must be listed. And now, when I'm propagating derivatives backwards, here's what I need to do. I know I'm going to get derivatives for the maps, all of the transform maps. But I know all of those were generated by a single kernel, right? So I'm going to have to transform the derivatives backwards through the function that actually transformed the kernel itself before I aggregated the derivatives. And so as you can see, this will introduce beautiful transform invariance. It's computationally infeasible. Given a choice between doing all of this work and simply using a somewhat larger network and augmenting your data, what would you do? Augment my data, right? Or, yes. Yes. Can you read out the question?
Instead of rotating the filter, could you just have all points with the same radius from the center of the filter to the same path?
So instead of rotating the filter, can you have all points in the within a radius have the same value? That's, if you did that, then what kinds of patterns would you be able to recognize? You'd only get radially symmetric patterns, right? The filters can be arbitrary shapes now, so you don't want to impose constraints on the filter. So you actually want to be performing transformations of this kind. This is something you would never do. Now, we're just introducing the notion of shift invariance so that you get an idea of transform invariance so that you know that this can be done. But practically speaking, it's a silly thing to be doing because the computational expense and the memory expense, right? Each filter is now going to produce so many channels. It just makes the whole thing not worth it. So although this mechanism does exist in principle, in practice, you're not going to see it, right? So extending it, CNNs are shift invariant neural network models for shift invariant pattern recognition. The parameters of the network can be learned through regular back propagation. And of course, like regular MLPs, individual layers may increase or decrease the span of representations used, which means that you can increase or decrease the number of channels as you go through the convolutional network. But the key bit is this: the models can be easily modified to include invariance to other transforms, but these tend to be computationally very painful, right? So that's one. Now, all of this was focused on a specific kind of problem. Does this picture contain a flower, right? But suppose I also want to know where is the flower. How can I do that? Right? It's not enough for me to say that this thing has a flower. I want to know where the flower is. Are you going to change the model entirely, or will we continue using the same model and try to do something extra? The information, does the output of the convolutional network contain information about the location of the flower? It does, right? You're scanning, and when you're scanning, the pattern is going to get highlighted wherever it is located. So if you look at the output of the final layer, in there is information about where the pattern might reside, right? So what you would typically do over here is to say that after you flatten the final layer, I'm going to have two separate operations. The first one just performs classification to detect if there's a flower or not. The second one computes the coordinates of the bounding boxes of my object. And so I can just use the same features to compute the bounding box, the corners of the box within which the object lies. You can scale it up to any number of objects. That gets a little more complicated. That's where YOLO and RCNN come in. But the basic principle is just this. And so when you train the network, you're going to train this with two losses. The first one is the Kullback-Leibler divergence for the classification layer. And the second loss is going to be a loss derived from the bounding box. Now you can just use an L2 loss. How wrong are you in computing each of the corners? Or you can use something more appropriate for this problem, like an intersection over union loss, which determines whether the size of the box and the location of the box match the target properly. Yes, Katrina?
Just a quick question. When you're training the model, you need to provide both the pictures and labels.
You would need to, so to train this, you would need to provide the bounding boxes, right? It's not completely, it's not implicit. You would need data of this kind to learn the model, right? But then if you're doing this, the same model can now be used for other kinds of things. You kids are too young. You've been here, you haven't been here long enough, but if you were here before COVID, anytime you walk down the hallway from Gates building towards Newell Simon Hall, at the end, there was a big screen. And Yasser Sheikh had this demo over there where he would draw your skeleton as you walked. It was kind of spooky, but it was brilliant. It nailed it. You know, you'd be walking, you could be wiggling your fingers, you could be dancing, you could be doing anything, and it would draw your skeleton exactly where your shoulders were, where your joints were. Occasionally it would get tangled, but that was rare, right? And so something like that. Now imagine that figure to the left, except that's being drawn continuously as you move. How would you do this? Turns out you can do the same thing with a CNN. A human being has only so many joints, right? All you need to do is to find the locations of these joints. And the same mechanism can be used to find the locations of these joints. And so you can draw this figure, right? So this is something that you guys could do too if you had the training data for it. Time's up. Okay. Time's up, guys. Pokemon War Turtle. What's the answer to the first question?
True.
Thank you. Pokemon Blissey. What's the answer to the second question?
True.
Thank you. And Pokemon Mook. What's the answer to the third question? Muck, Mook, M-U-K.
Also true.
Also true. Okay. So all of them are true, right? To find the position of an object, we need multiple output layers. One to identify the class and the other to predict the position of the object. The CNNs are invariant to the position, but not the orientation or scale of the target pattern. To make them invariant to a transform versions of every filter must be included in the model for every transform considered. So it's not just rotation invariance, it's just not reflection invariance. If you want scale invariance, you're going to have scaling up and scaling down as part of the set of transforms. You wouldn't really do it. So now this sort of covers the gamut of the various things we can do. You can have many variations. You can have very deep networks, 100 or more layers in an MLP formalism called ResNet, or you can have things like depthwise convolutions. Let's just quickly go over these. Depthwise convolutions are particularly interesting. So here's how we performed a typical convolution layer. You had a filter. The filter had as many channels as the input. And when you convolved, each channel of the filter scanned the corresponding channel of the input, right? And so each channel of the filter produced an output map. And then you added them all up to get the final output channel. That's basically what we were doing. And so if you had many filters, each of the filters would have many channels. So each channel of each filter is going to produce an output channel. And so if you had these three filters, the red, green, and the blue filters over here, then you're going to be computing if you have, say, four input channels, these figures are kind of messed up. There should be as many input channels here as the number of channels in the filter. You're going to get as many convolutional outputs as the number of input channels, and then you're going to sum them all up to get the corresponding output affine map, right? Do the same thing for the second filter. You're performing as many channel-wise convolutions for the second filter as the number of input channels itself, and then you're adding them up. And so you do this for every one of the filters. For each filter, you perform as many convolutions as the number of channels in the input. Now I can this makes things expensive, because if I have n filters and if I have m input channels, how many convolutions am I performing? N times m, right? For every one of the filters, I'm performing a convolution over every one of the input channels, right? Can we save on the computation? Now, if you're doing things on a small device, you don't really want to be performing all that computation. And we know that even training these models gets to be very expensive, right? So depthwise convolution does something just slightly differently. You use just one filter, and that way, if you have m input channels, you're going to perform just m convolutions. But then you don't just add them up. You perform a weighted addition. And the different output channels are obtained as different weighted sums of these channel-wise convolution outputs. So here, I'd have this one common filter. I'm going to convolve it. I'm going to get the results of the channel-wise convolutions. So I'm going to get as many channels as the number of input channels itself. But then when I sum them up, instead of just doing a direct sum, I'm going to perform a weighted sum. And different weighted sums will give me different output channels. So this obviously doesn't have the same expressive power as the full convolutional network, but then it's going to perform far fewer convolutions. Instead of doing n times m convolutions, you just perform m convolutions, right? The number of parameters is also going to be much smaller. So if you compute this, if there are m input channels and n output channels, if there are, say, each filter is k cross k, then the number of parameters is going to be, each filter is going to have m times k squared parameters times n is the number of filters, and m k squared parameters. Whereas this one here, I just have one convolution, which is going to be mk squared parameters for the convolution, and then for the weighted sum for each of the output channels, I'm just going to have one set of m weights for the output channel, so n times m parameters. So if you come look at the number of parameters, this can be orders of magnitude and difference in terms of the number of parameters as well. So these depthwise convolutions end up being much cheaper to compute and also require far fewer parameters, potentially making them more robust and simpler. Now, it just turns out that everything comes at a cost. And so when you save on compute and you save on the number of parameters, you typically give up something in performance. Right? Questions? MobileNet this uses depthwise convolutions, but many other models use them too. Yes, Stefan.
So we have this one single filter with like the same number of channels as a number of input maps, and then we just take different weighted sums of that same.
Yeah, pretty much, right? So you perform the convolution, then retain those output maps, keep them separate, and then perform and then compute different weighted sums of those guys for the output channels. Now, yeah. Time's up, guys. Pokemon Eevee, what's the answer to the first question? Eevee?
False.
False, thank you. Pokemon Ariados, what's the answer to the second question? Ariados? True.
It's true.
Thank you. So does everybody agree? Uh-oh. The first one is, why does this do that? False, and the second one's true. Filters in depthwise convolution convolve all the input channels simultaneously and sum the result. That's false. Depthwise convolutions require far fewer parameters in computation than regular convolutions. This is true, right? Now, what do the filters learn? Now, for the neurons in the first layer, you can just look at the patterns of weights. And the pattern of weights is what the pattern that the filter is looking for. For filters in later layers, it's very hard to determine exactly what pattern it's looking for, because as we know, these are Boolean operators. They could be performing and or complex Boolean operations. And so the specific pattern that made them fire can vary from input to input. So for any given input, you'd have to work your way backwards from the output of the filter to figure out what portion of the input made it fire. And for that, you'd have to backpropagate the derivatives to see which portions of the input, when perturbed, modify that particular output most, right? And so if you do this, you'll actually find what each of these things learned. What is happening here? So here are some examples. So these are all networks learned on different object classes. Observe something very interesting. Actually, I think this was a single network, and they're showing the responses to different types of inputs. Now, in every case, observe that the lowest layer, the first layer of the network, learns some interesting patterns. What do these things look like? If you go back a few classes, remind you of something? The stuff that the eye determined, right? The million eyes seem to recognize. This goes back to Hubel and Wiesel's original experiment. So amazingly, this experiment actually, this first layer of the CNN bus ends up learning filters which look a whole lot like the patterns that the human eye itself recognizes, which is so amazing, right? Or the mammalian eye recognizes. And all we've done is to train a shift invariant model. It turns out that shift invariance is the key to the kinds of patterns that our eyes key in on, right? Isn't that amazing? And then if you go up, if you're recognizing faces, the lower layers of the network begin firing for parts of faces. And the upper layers begin firing for different kinds of face-like patterns. If you're recognizing cars, the lower layers fire for parts of cars. The upper layers begin recognizing different kinds of car-like shapes. So in every case, it's building up the patterns. Parts of elephants combining to entire elephants, parts of chairs combining to entire chair-like shapes, right? And as you keep going later and higher into the network, you find them being more and more specialized to specific, very target-specific patterns. It's pretty amazing, right? Now, when you train these things, you get standard convergence issues. You need to add other momentum style algorithms, and the number of parameters can quickly become very large. So data augmentation is something that we're going to use. You've all encountered this. Data augmentation over here is typically done by distorting your input a little bit, scaling it, rotating it, adding some noise. Anyway, CNNs, they're used everywhere. Originally, they were designed for images and things like speech, right? But 1D CNN was used for speech. In fact, these days, we just convert speech to spectrograms and use two-dimensional CNNs. But here's the crazy bit. CNNs are also used to process text, because you can just think of the string of words as a sequence of vectors, and you can use them to process text. You can use them pretty much everywhere, and they seem to be very effective. So this Andrew Karpathy has so many nice demos. This was from his days at Stanford. Now, what are some classic examples of CNN successes? The oldest one, of course, was Jan LeCun's LayNet. We saw that. But CNNs didn't really become a big deal till this paper on ImageNet classification. ImageNet is this task many of you might have encountered, which is a large-scale visual recognition problem. You have thousands of classes of images which have been collected from the internet, and the problem here, you have about 1.2 million pictures. The task is to classify these into one of 1,000 categories of objects. That's a large number, right? So not unexpectedly, it's challenging. And for the longest time, the best performance had something like 25% error on ImageNet. Until along came this paper, AlexNet, in 2012 by Krzyzewski, Satskeva, and Hinton. And the model that they originally proposed was this big CNN. The model was so big that it didn't fit in the paper. And so even in the paper, the upper portion of the picture is cut off. They distributed it over 2 GPUs. These days, it probably fits on your wristwatch or something. But back then, it was too large for the GPUs of the day. Lots and lots of parameters. But that's just some details of the kind of things they did. They introduced a whole bunch of ideas, like when you classify, why do you just classify a single image? Since you have shift invariance, I can crop the image in many different ways and classify each of these crops and vote over the lot, right? You can change various things. So they introduced the notion of early CNNs just use sigmoids as activations. They introduced the notion of using ReLUs. They introduced various other little tricks which helped, which we still use. And they found that the final top 5 error was 18.2% with a single net, which fell to 15.4% when you ensembled 7 networks. This is down from 25%, right? Huge step. And again, when you analyze what it learns to detect, the lowermost layers end up detecting very mammalian-like patterns. And they found something even more interesting. The penultimate layer of the network learns a feature representation on which you perform classification. If you just analyze those, so here are some typical errors. They find that even when it makes errors, the errors are not particularly bad, right? So this is supposed to be a mushroom, but it's The mushroom comes up second. This is supposed to be a grill, but obviously the grill is on a convertible, so it recognized the convertible. This is supposed to be a cherry, but it found the dog, right? I can't blame it. And this is 2012. But more importantly, the representation learned by the final layer turned out to be class specific. So they could just use those representations to perform retrieval. And so if you presented the network with, say, a jack-o'-lantern, took the final layer representation and searched the entire database, it just pulled up more jack-o'-lanterns. So this is the basic concept that we use these days for your homework too, for face verification, because the representation itself ends up capturing this behavior, which is amazing, right? And then, of course, people began working on it. Within a few months, Zeiler and Fergus brought the error down to 14.8%. These guys, VGGNet, which is still being used, brought that down to 7%. Then it went down to 6.7%. ResNet, which all of you have used, accounts for the fact that back propagating derivatives through convolutional layers has issues if you have too many layers. So they bypass it by having a residual connection going forward. It brought the error down to 3.5%. Now the error is in 1% or thereabouts. Now from 25% to about 1%, just using convolutional networks. So you see how effective these things are. Many more architectures, and also used for speech recognition. Anyway, I'll stop right here. That's the last of our lectures on convolutional networks. Next week, we will begin talking about recurrent neural networks. And homework 3 is all about recurrent neural networks, right? 3 and 4. Thank you very much. I'll take questions on Piazza.